Hey, how's it going? We're looking at the mole review. This is going to be going over page 1 of the review. I want to start first by showing you the completed answer key for page 1. So check your answers. If you were a little off, you may want to go back and look at how you rounded your molar masses to the hundredths place. If you were way off, you want to stay tuned as I go over each problem. Alright, and here's the rest of the page. Alright, so going forward, if you had particular problems, you could navigate your way through the video to the problem that gave you some issues. Let's start with question 1, finding molar mass. To find molar mass, you do need the periodic table. You will need to look at each individual element and you will need to round properly. So I've gone ahead and shown you what I've done. Periodic table tells us the molar mass for each individual element. That's the number of grams there are in 1 mole of each of those. Now when we look at compounds, we just take each element and multiply it as according to its subscripts. You can see there's only 1 magnesium, 2 nitrogens, and 3 times 2 oxygens. Finding each piece is especially useful later when doing percent composition, but we're really interested right now in the total. So you can see the same thing for number 2, or I'm sorry, for letter B of number 1. But be careful how you count, because there are 2 N's, 4 times 2, 8 H's, only 1 carbon, and 3 oxygens. And you can see the work that we did there, for a total of 96.11. Finding the individual molar masses from the atomic mass on the periodic table, rounded properly to the hundredths place, multiplied by the quantity of each atom, and summed for the total. When you do this on the calculator, you could actually just do 14 times 2, 1 times 8, 12 times 1, 16 times 3, all added together at once, and hit enter at the end. So 14 times 2 plus, 1 times 8 plus, 12 times 1 plus, 16 times 3, enter for an answer. But when doing percent composition, be sure to get each individual piece. Alright, moving on to molar conversions, question 2. We started with 23 moles of lithium hydroxide. And you can see we don't want moles of lithium hydroxide, we want grams, the mass, how many grams there are in that many moles. Well, to know how much 23.0 moles would weigh, we need to know how much 1 mole would weigh. Well, we know we could find the molar mass of lithium hydroxide, just as we did in the last 2 problems. 1 lithium, 1 oxygen, 1 hydrogen, summed up, tells me that for every 1 mole I have of lithium hydroxide, it weighs 23.95 grams. Of course, you can't do this conversion or use this conversion until you've actually calculated it using the periodic table. So this does require that additional step. Now that you have the mass of 1 mole, multiply by 23 moles to find the total mass. Top times top divided by bottom, 551 grams of lithium hydroxide, once our units or our labels factor out. Alright, question number 3. How many moles does 80 grams of water represent? Well, we're starting with 80 grams of water. We don't want grams of water, we want to know how many moles. So we need some kind of relationship telling us how many grams are in 1 mole of water. Well, again, just like we did in number 1, we could find the molar mass of water. And this is one that you want to remember because it's one you're going to use a lot. Hydrogen, there are 2. Its molar mass times 2, and oxygen's mass times 1, for a grand total of 18.02 grams per mole of water. So for every 1 mole of water, it has a mass of 18.02 grams. Well, I know that 1 mole is 18.02 grams, so I know I have several moles here, and 80 grams. 3 sig figs require 3 sig figs in the answer. That's why I did have to round the last one as well properly. Here we're doing 80.0 times 1 divided by 18.02 equals 4.44. Again, this conversion factor relating moles to grams mass can only be obtained by using molar mass in your periodic table. Now question 4 as well as 6, I'm going to assume that the term atoms should have been molecules and correct that for you. So question 4, how many molecules are in 0.25 grams? So, oh sorry, 0.25 moles. So notice there's no mention of grams, so you're going to actually see there's no need for the molar mass of this. In fact, this is really not that relevant to this problem because there's no mass involved. We're basically asking how many items are in a quarter of a mole. In this case, the items are molecules. Well, I know I start with 0.25 moles. So the question is, how many molecules do I have? Well, to answer that, I need to know how many molecules are in 1 mole. And I know Avogadro's number says that there's 6.02 times 10 to the 23rd molecules or items in 1 mole of anything. So that 0.25 times this number, Avogadro's number, divided by 1 gives me essentially what is a quarter of a mole. 1.5 times 10 to the 23rd molecules. Question 5 as well mentions moles and molecules, but does not require the use of grams, so finding the mass of this is unnecessary. Now if they mention grams, then we could use it. So 1.2 times 10 to the 24th molecules. Well, how many moles is that? So if I have this many items, how many moles do I have? Well, again, I need to know Avogadro's relationship that says for every 1 mole, it's 6.02 times 10 to the 23rd molecules. So if I have this many molecules divided by Avogadro's number, top times top divided by bottom, tells me I have, when rounded to proper number sig figs, 2.0 moles when this many molecules are present. Now question 6 is a molar conversion that relates both mass in grams to moles to, again, changing it to molecules. Well, so this one you're going to see is potentially a 2-step problem. We could see the difference here. Because we are starting with 22.87 grams of sucrose, and we want to know how many molecules there are, we could go from grams to moles because we have a relationship from the periodic table that tells us how many grams are in a mole. And we could go from moles to molecules using Avogadro's number. So here's what I mean. According to the problem, they've completed the molar mass of 12 carbons, 22 hydrogens, and 11 oxygens and told me that for every 1 mole of sucrose, I have a mass of 342.34 grams. Well, stopping there would tell me how many moles I have given this many grams. But the question is not how many moles I have, it's how many molecules I have. So now that I'm in moles, I could take that and convert it to molecules, as long as I know a relationship that tells me how many molecules are there per mole. Well, I know that for every 1 mole, there's 6.02 times 10 to the 23rd molecules, canceling out moles and giving me the unit I want of molecules. So the math would be 22.87 times 1 times 6.02 times 10 to the 23rd divided by 342.34 divided by 1 for a total of 4.022 times 10 to the 23rd molecules. Well, you can see this mass is way less than a mole. So the number of molecules I have should be way less than a mole. And it appears that's consistent. Now you can also treat this as one step had we put the number of molecules directly over grams, relating it directly that way. Alright, last two, questions 7 and 8, both deal with percent composition, which are very similar to finding the molar mass. Question 7, letter A, you can see what we had to do. We had sodium, and there was 2 of them. Its individual mass times 2, sulfur mass, individual mass times 1, oxygen's individual mass times 4, and I found their individual pieces as well as a total mass here. So you can see how it is necessary now to do the individual parts, because I need to then relate these parts to the whole. You can see that oxygen makes up the biggest chunk of it, then sodium, then sulfur. We could see, it's about a third, which seems consistent here, times 100 gives us the percent. So part sodium over the total times 100. Now what part was sulfur? 32.01 over the total, so less in percent than sodium. And oxygen making up the biggest chunk of 64 out of the 141 total, 0.99 times 100, 45.07%. Now when you add all these up, just because of rounding, you do get only 99.99%, but that occurs rarely, still proving we've done this correctly when these add up to 100. Silicon dioxide, same idea. One silicon, its molar mass in the periodic table times 1, oxygen's molar mass rounded times 2, giving me each part, giving me the total. I could find the part silicon over the total times 100, and the part oxygen over the total times 100. You can see they're both close to equal parts, with oxygen being slightly more than half. Consistent here with a sum of 100% for both percents, verifying that we have done this correctly. Now number 8 is same idea, find the percent composition of water. Now this compound here, you may have noticed this dot, seems a little weird. That does not mean you multiply, it just means that these are all chemically bonded. This is referred to as a hydrate, a compound that just has water chemically bonded in it. Well, we know the molar mass of water is 18.02. And so in this case there are 7 water molecules, which tells me the total mass of water in this compound. I could then continue finding the masses of zinc, sulfur, and 4 oxygens, which I've done, to give me the grand total of this entire hydrate. So I know the total of this hydrate, including those 7 waters. I want to know what percent is just water. Well, the part water is 126.14 over its total of 287.59 times 100. Does give me a final percent of 43.86% that is water. No need to find the percent zinc, sulfur, or oxygen, although I could. They just wanted the percentage of water in each compound. So that completes the review. Page 1. Hopefully you all could verify that you've done this correctly. Continue with page 2.